Okay, so without further ado, I'm going to go ahead and introduce our first speaker for the paper session, Arjun. Arjun is at Databricks, and he will be presenting a talk entitled Threat Detection on Kubernetes Logs Using GNN Embeddings. So let's go ahead and welcome Arjun to the stage.
Hey everyone, my name is Arjun, and thank you, Sagar, for the introduction. Welcome to my talk. It's titled Threat Detection on Kubernetes Logs Using GNN Embeddings. So let me start off with a quick introduction. So I work at Databricks on the detection engineering team. Primarily, my focus is on sort of using ML techniques to do detection, and kind of done similar things at other places like NVIDIA, Guidewire, and Home Depot. So that's sort of like this area's been sort of what I've been concentrating on for the last few years. The agenda of my talk is it's kind of twofold. I think one of them, obviously, at the very beginning, it's so much about how we can use Kubernetes logs, how we can model them as graphs. The second part is a little bit about me sort of philosophizing about how threat detection, in spite of the fact that we've made a ton of advancements in machine learning and using it for threat detection, it's so much about sort of doing the basics right when it comes to things. And a lot of this talk is about sort of me walking through using machine learning models for threat detection and then sort of trying to figure my way out of it once I've actually deployed the model and trying to find like relevant threats and alerts. All right, so let's get started. So this is the initial problem statement. And when I was sort of creating this particular slide, I didn't mean for it to be a wrap on traditional detection rules. I am a fan of traditional detection rules, and I still think they offer the most value when it comes to detection engineering in general. There are some problems associated with rules. Rules are, they're good as long as they're good, but then you end up sort of spending a lot of time tuning them. You spend a lot of time building out exclusion lists for rules, and folks with experience with SIMs or such sort of tools are probably very familiar with it. I think one of the problems that I've faced with rules is obviously the fact that you can't really sort of encode any sort of structure in it because you're sort of trying to sort of build out heuristics. Baselining is really hard, and I think sort of the one perennial problem in security ML is you have no label data, and I've been sort of parroting out the no label data sort of aspect for close to 8 or 9 years now. And in spite of the fact that I work very, very closely with the incident response team at Databricks, I think one of the problems we do end up facing is like it's really hard to label data at different points in the application. Specifically, when I work on this talk is titled on K8 logs. A lot of times, you don't really have traditional malicious/benign labels for things in part of the application that when you're somewhere in the middle. So it's kind of hard to build out a supervised learning problem in itself. So this is kind of like sort of what my life is all about. Like, you're trying to build rules, you're trying to build machine learning models, you're trying to sort of make the detection process faster, easier, and sort of trying to lower the signal to noise ratio. So before I sort of dive into sort of the modeling side of things, I want to sort of start out with a quick primer on K8s or Kubernetes logs, servers, and sort of all the associated infrastructure. So for folks unfamiliar with Kubernetes, it's basically an orchestration platform which you're using to sort of scale and sort of work with a lot of the applications, especially popular in I would say like the modern application stack. There are two aspects of the Kubernetes infrastructure. One is the control plane, and the other is the data plane. And we will be focusing mostly on the control plane side of things because that's where the logs that are generated, the Kubernetes audit logs, are used for security monitoring. Also, within the within the Kubernetes control plane, there are lots of different components. You have the scheduler, you have the controller, you have the control manager, but the star obviously is the K8 API server, which is kind of, you could call it as like the captain of the ship in terms of how it controls resources, how it sort of coordinates between different resources, and of course is responsible for collection of the logs itself. So it kind of tries to answer the following questions, right? Like what user is sort of generating the traffic, why are requests being rejected, who's accessing what sort of production features, and is there any way we could actually find malicious activity? This is slightly different from, a lot of the CNAP stuff that you see with various vendors where, they have agents on the containers themselves. That's sort of a different aspect. This is sort of more on at a slightly higher level where you're looking at just the audit logs associated with stuff happening on the control plane. And I would say most of the stuff happens on the control plane. And another aspect of this is the fact that these logs are very high volume. So as a detection engineer, when just like Databricks, most of our infrastructure is K8 based. So you're basically getting a lot of high volume data from a lot of different data sources. And it's hard to build rules out of them without, sort of just spamming the incident response team with alerts. So this was like a necessary challenge in terms of like, hey, is there a way I could find context and structure within these logs to sort of make the lives of detection engineers and IR folks better? Okay, so this is kind of like an example of what a K8 audit log looks like. It's pretty granular, but I've sort of tried to divide it between like 4 different sections. One is, you have like a user or a system group sort of trying to request for information from a resource. There is a response associated with it. You'll see like certain metadata components, such as the timestamp and the audit ID. The annotation section is really useful because it sort of gives you extra information about what the user is requesting for. And of course, there are various different logging stages. If you look at sort of, something I mentioned earlier, that K8's API audit logs they're very high volume because almost every stage in the process is logged. So you have request received, started, completed, which, for even like a small Kubernetes session can generate like thousands and thousands of logs. The other aspect is the schema is really bad, to be fair, but I kind of cleaned it up. But if you look at the request information and the response sort of information that is sort of given out, it's basically just like a struct type blob where you end up having to write very complex queries to get things out. What sort of caught me when I was, I guess, spending like an inordinate amount of time staring at these logs was the fact that, there is like an action or a verb type. And I think that's really useful when it comes to sort of looking at the logs itself, because you get like an end response to like what the user at that point is sort of doing or trying. It also gives you an information about like, if I have this user is accessing like a resource, what kind of response is sort of being given to that user. So this is what the audit log looks like. And, the next stage of the talk is sort of a little bit about like how I wanted to structure these logs themselves, like, because of the high volume and stuff. So I wanted to title this slide as what is a K8 session? And I was afraid that someone would ask me like what the formal definition of a K8 session is. And then I Googled around a lot yesterday night, and there is no formal definition. So this is my definition. It kind of went by the wayside when I was trying to figure out like how do I define or aggregate data, right? Because that's what I'm looking to do. I'm looking to see like if I have X number of logs over a course of 1 minute or over a course of an hour from various different systems, like how do I aggregate them? So if you look at the diagram here, you have basically a set of IPs in the control plane. So those set of IPs could be external or internal, depending on how your application is structured. You have, in the case of, let's take for the example of EKS, you have a user group, you have a AWS name sort of given to it, which sort of acts on the namespace, and which then you're sort of going over to the resource and asking for something, right? So a lot of times with Kubernetes, you'll see folks going and creating system service accounts, and those system service accounts are the ones that are sort of acting on the resources and trying to basically do things. And when I say do things, it could be it could be on like pods or nodes. You're generating something, or you're patching something, or you're deleting a resource. It could be n number of things. Again, when I was sort of creating this diagram, I wanted to make it look fancier, I guess, but I couldn't, because there are lots of interdependencies between like the different user groups and names, which is a little more difficult to sort of showcase. But there are user group 0 could be working on sort of namespace 2 or resource 2 as well, and the same with like all the other groups. But when I was sort of looking at the data itself, I think the one thing that sort of stood out for me was the fact that the verb or the action, there is always a verb or action associated with every sort of response. So aggregating like multiple such records associated with a time granularity and the action in itself was what I was sort of going for. So the different types of verbs or actions are, like I mentioned, it could be get, it could be patch, it could be delete, it could be sort of 6 or 7 types that you generally see in a Kubernetes application, but that sort of depends on how your infrastructure is also set up. So now we sort of, before I dive into the model, I wanted to sort of put in like a very high level view of what I was thinking. The goal was, how could I structure these K8 logs, and how could I sort of derive information out of these logs based on the structure that I sort of create. So what I did was I have K8 audit logs sort of going into graphs that I create. And I'll talk about like how those graphs are created and how the relationship sort of comes in. Feeding into a GNN model, which would end up sort of classifying these graphs based on the verb type. So when I was creating the session itself, my session was based on a particular time granularity, as well as the verb or the action in the end. Kind of ends up becoming like a multi-label graph classification problem. I have around 5 verbs shown here, but it could go up to 6 or 7, which is the case in the application I have. The goal was, once the structure of these sessions is learned, I could then use those embeddings that are generated for downstream anomaly detection tasks. So you could have the time duration or the interval over which you aggregate. Now that depends on your incident response team and how easy it is for them to sort of respond to things. So if you think like, in my case, the aggregation interval was for a minute, but you could have it for an hour. It really depends on like how easily you can create those graphs and what is sort of the time step for the response side of things as well. So now I sort of go into sort of why I was thinking that these audit logs could be sort of structured as graphs themselves. That's because there's a very natural connection from the IP side to the final decision, right? So you have an IP associated with a system user group. Every user generates a request. Every request is routed to a resource, to a final decision based on the resource that you're sort of hitting. So the goal was, can we have a set of nodes associated with the IP? You could have some sort of aggregation or grouping within the IPs. The user group, the request object, the resource, and the decision. So you'll have, basically you could create multiple such graphs based on sort of a time interval, which you would help to define a session. Each session would be considered a graph, and each session would be associated with a verb. So you're basically sort of parsing through the graphs, extracting information associated with a verb and then structuring them as a graph. I sort of went in with a very sort of simple feature matrix. I had a 40-dimensional feature matrix associated with each node, and I just used a simple feature hashing methodology on the string name to get the feature matrix itself. The verb was basically the Y label, which was what I was classifying on. So the goal was basically I'd have thousands of graphs basically based on these aggregated time intervals that I would sort of create things on. So what I sort of ended up doing was using a graph convolutional network. So folks familiar with GNNs would know that the GCN is probably like sort of the go-to methodology when you're sort of creating like a graph neural network. It has the philosophy of a convolutional neural network, just the idea of the basics of how GNNs work with, with graphs and the fact that they can generate node embeddings. I went in with a 3-layer GCN. You could kind of try out various different sort of structures, but the more layers you add in a GCN, the more hops it has to take when it comes to aggregation and parsing. So it becomes, so your embeddings could get a little diluted if you make a really deep neural network. And in this case, I had lots of data, so there was no problem on that end. So I could sort of figure out a pretty good strategy with just a 3-layer GCN. And the node embeddings generated were then sort of passed through sort of a global mean to generate embeddings associated with the graph itself. What you could see here are sort of, when I was sort of looking at the training set, kind of hard to figure out how good my embeddings were. So this is sort of a TSNE-based distribution of embeddings before I actually set about training them and after. And you could say that it does, apart from the fact that, you could look at sort of the labels itself on an evaluation data set, sort of plotting the embeddings on a 2-dimensional graph based on TSNE at least gave me an idea that, it was working kind of. And the fact that all the 7 labels that were associated with the different verbs were sort of broken down into different spaces in the 2-dimensional data set. But again, there is, with TSNE, using that for sort of dimensionality reduction can always get a little tricky, but this was sort of more of a sanity check than anything else. I also ended up sort of trying out 2 different evaluation samples of close to like 9,000 graphs on 2 different data sets, which were very different from the data that I'd sort of trained on, different regions and different services itself. You could see it kind of struggles with these labels 6 and 7, which are associated with patching and deleting, which I wasn't surprised about because we didn't have as many samples associated with those 2 labels in the training data set itself. It does pretty okay, I would say, on the sort of the other labels itself. So very quickly, I think this was the section that kind of was the hardest for me, and I feel like is always sort of the hardest section for detection engineering using ML. I had this very wise colleague who told me when I was sort of working on this section, I was like, maybe I'll generate some fake data which would look like an alert, and then I would have my model alert on it because that's kind of what we'd end up doing. But the data that I would end up sort of creating on the adversarial side would be fake. It wouldn't really be representative of what I do on an everyday basis. A lot of the stuff that we detect, as sort of Sean had sort of mentioned, when you're on the blue team, you have to be right 100% of the time. And a lot of the stuff that we do detect sometimes is not right, or sometimes it's just about hygiene. You have a user sort of going around trying to exec into a pod when they really shouldn't be. So instead of sort of creating fake data, I sort of went in with kind of what I had. We had the embeddings generated here, and you'll see on the left, I have the container, sort of the MITRE attack matrix for containers, and you'll see a lot of the common use cases, such as listing of K8 secrets or Kubernetes cron job detection. a lot of these can be detected by rules. So I always figured that the machine learning based models that we use for detection are kind of like umbrella models. You can sort of you can almost never match them to a MITRE attack framework because it just doesn't make sense. You can use rules to find them. So it'll kind of tell you that something is off, and then you can have like a bunch of rules that you'd correlate and sort of provide something actionable to IR. I've had a lot of cases where I've been called into an IR Slack channel with someone yelling at me because my rule went off or my model went off, and which is why I do believe that the correlation aspect of using machine learning and rules is really important. Infrastructure is prone to malicious attacks, but it's also prone to, like I said, really bad hygiene. Willie from engineering shouldn't be logging into prod ever, but it is what it is. So how do we use the embeddings downstream? Now, there are various ways of using embeddings downstream, and it's kind of hard to find like a really good way to evaluate it with a really good data set, which I did not have. So I kind of went with what I had without generating the fake malicious data that I thought I would. I basically trained an isolation forest on my training embeddings and created an evaluation data set of around 420 graphs, which is about data connected from like an hour on our production data set. And I wanted to see when I used an isolation forest on those embeddings, what would I find? So this is kind of like sort of a PCA-based distribution of what I found. I used a very, very low contamination factor, and I was looking at basically the 99th percentile of my isolation forest results to see like what are these anomalous events. I picked PCA because generally you could pick sort of any way to sort of do dimensionality reduction, and it sort of gave me a good view of the benign versus what is the anomalous data points. Remember, there are only 420 data points here, and they're low. The number of data points are low because whenever I'm working with the IR team at Databricks, they need information within a specified time period. So I can't be running this model once a day or once every 2 days. It has to be running on a streaming inference, and it has to be running continuously. So at least within a 1 hour time frame, that's sort of enough information and enough of a time period. So how do you actually sort of evaluate if the anomalies are legitimate, right? Because you basically have like a bunch of numbers, and how are you sort of going to sort of go about it? So you look at some things such as unusual number of nodes, source IPs, or the namespaces associated with it, and the usernames as well. So I feel like at the end of it, whenever you're sort of looking at the results of anomaly detection and embeddings, you still end up doing a lot of commonly used threat detection techniques because you end up having to roll back from the embeddings onto the data itself. So you're sort of digging into the data that your machine learning model is sort of telling you, saying, hey, this is bad, but why is this bad? And in this process, it was bad because we weren't communicating with engineering. They had created a new hardening process, which had initialized a bunch of new IPs, a bunch of new namespaces, and a very strange looking username that I had no idea about. And it was a benign true positive, but I do feel like the model was doing what it was supposed to be doing. It was finding anomalous activity. But sometimes it's not so much about, hey, there's a bad actor doing really bad things. Sometimes it's about anomalous processes that are created because you're in a very big enterprise and sometimes teams don't communicate with each other. In the end, this was, thankfully, if it was really bad, I wouldn't be here talking about it, but it wasn't. It was just a bunch of sort of new IPs associated with the hardening process, a new username, which was kind of slightly different from what it was. And because of the new hardening process, the size of the graph was really small as well, which kind of popped off on the anomaly detection side of things. And just to end it all, challenges with machine learning is, kind of very common that you see here, interpretability. And like I said, an anomalous event is not always malicious. I still believe that, you still have to do very good red teaming to make adversary simulation realistic. And not all enterprises have the resources to do very good red teaming. So it's kind of, when you're sort of testing out these models, a lot of it has to do with the fact that you sort of go back into the data, figure out what's there and what's not, and make sure what you're doing is sort of correct. And yeah, work with your IR or SOC team to tune the models at a very consistent cadence. And yeah, shout out to the detection and response teams at Databricks who have helped me with the whole presentation. Thank you.
Yeah, thanks for the talk. I'm curious what motivated the graph neural network approach. Like, did you start with, running isolation forest on the raw features and, or on, like a PCA dimensionality reduction and sort of work your way up to GNNs? And how well did they perform, over those sort of simpler baselines?
So we start off with just rules. We just had a bunch of rules associated with the MITRE attack framework. We then moved on to, like you said, we used an isolation forest. I've also used transformer-based techniques just to sort of use like a fine-tuned transformer to look at the logs itself and generate embeddings out of them. With the isolation forest, the results weren't as good. With the transformers, because the number of logs are so many and such high volume, generating the number of embeddings at scale was very, very difficult. What I could do with GNNs was I could aggregate information associated with the logs over a time interval and generate an embedding based on a structure itself, which was a very natural structure. So that's kind of what made me sort of go to the embedding, the GNN side of things.